welcome to my YouTube channel. Today we are going to discuss thermal dissipation and heat sink. Now thermal dissipation. To understand thermal dissipation, let us take an example of current flow. This is a node A with potential VA and node B with potential VB. Whenever there is a potential difference between two nodes, a current flows from A to B. That current flow is given by Ohm's law. This is the expression. Now, similar to the current flow, there is a flow of heat. This is a junction at temperature Tj. This is another node, that is ambient surrounding temperature Ta. So whenever there is a difference in temperature, power will be dissipated, and that dissipated power is given as this formula, which is very much similar to current flow. Instead of potential difference here, we have temperature difference here, and instead of normal electrical resistance, we have thermal resistance. So theta is notation for thermal resistance. Now the amount of thermal dissipation depends upon the maximum junction temperature Tj max, and this maximum temperature is defined by manufacturer, and it depends on reliability of a die used in manufacturing process. Now, with the help of these two parameters, that is thermal resistance and maximum junction temperature, maximum power dissipation can be calculated by using this relation. So it's the same as the previous relation, this one. Just we have replaced maximum power dissipation and maximum junction temperature. Okay, so this is PD max. Now when you look at the data sheet for any given transistor, you will find PD max in data sheet at 25 degrees Celsius, and beyond 25 degrees Celsius they specify how it derates, or this gives through a something called derating curve. This signifies derating curve. We'll go to that topic next. There is a maximum junction temperature given in the data sheet, and thermal resistance is also given in the data sheet. So you can see maximum power dissipation at 25 degrees Celsius, room temperature is given, maximum junction temperature is given, thermal resistance is given, and derating factor is given. This is common for most of the transistor. Okay, this is derating curve, Tj max. Okay, now let's discuss power derating curve. In power derating curve, we'll take temperature. This x-axis is cage temperature in degree Celsius, and y-axis over here is a power dissipation in watts. So here you see from 0 to 25 degrees, the power dissipation is maximum at 180. This value is 180 watt. Beyond 25 degree, this curve derates over here, and that decrease is controlled by derating factor, and the derating factor is calculated as 180, that is maximum power dissipation, divided by this difference from 150 to 25, that is this difference will give you 125 degree Celsius. So this is the value 1.44 watts per degree Celsius is a derating factor over here. So most of the data sheet will give you derating factor. At times you may find derating curve in the data sheets. Next is heat sink. Now in our discussion earlier we have discussed thermal resistance. This thermal resistance is made up of at least two components. This J represents the junction. Junction to case, it is theta JC, first component, and from case to surrounding to ambient, it is theta CA. So you have two components in thermal resistance. The first component is very low and it is controlled by manufacturer. From case to surrounding, you can add one more component. That component is called heat sink, and which will improve the power dissipation or increase the power dissipation. Now heat sink is a mechanical device connected to the case of transistor, and it will provide a larger surface area for dissipation of developed heat. Here I have taken some example. This is my random circuit over here. This is circuit, main circuit. To this circuit, can you see a metallic plates are connected? These metallic plates or individual blade is known as a fin, and this entire assembly is known as heat sink. You might have seen this in practical circuit. Second example is power supply, regulated power supply, commonly seen in your electronic labs. The back side of this over here, if you see a back side, you will find blades, that those are heat sink. So heat sinks are commonly used in power devices. Next is a thermal analogy of transistor. Now let's continue with that diagram. This J represents the junction. This is case, C is case, H or S is a heat sink, A is the surrounding temperature or ambient temperature. So you can see from case to ambient you have inserted a sink over here. Now when I want to calculate total thermal resistance, I'll add them. So this gives me total thermal resistance, and then power dissipation will be junction temperature minus ambient temperature divided by a thermal resistance. And from this equation you can calculate the TJ max equation or junction temperature equation for any transistor. Now to understand the impact of heat sink, let's take an example where all the values of thermal resistances are given to you, and junction temperature is given, ambient temperature is given, and we are supposed to calculate maximum power dissipation with heat sink and without heat sink. So the first case is without heat sink. So without heat sink means we'll have a junction to case to ambient. So in that case we add the values, so we'll get this as a thermal resistance, and you know this formula for PD max. Put the values over here, so you get this as a answer. PD max is 2.318 watts. Now when we use heat sink, sink is inserted between case and ambient. Okay, so this is a sink, heat sink. Now in that case total thermal resistance will be calculated by addition of all three. So this is your thermal resistance, add them, you get this. Use same relation again, but in this case you see power dissipation is more, it's 15.48 watts. So you can see by using heat sink power dissipation has improved or increased. Now, while selecting a heat sink, you need to take care of few parameters, because heat sink mostly depends on thermal resistance, which will depends on length and the cross sectional area of the heat sink that you are using, airflow, volumetric resistance, fin density, fin spacing, width and length of the sink. Thank you.